to do if the series is non-Gaussian? What to do if x, our observation, are not Gaussian? The first thing that you should do is take the logarithm. You can do that because our observations are positive. Before subtracting the mean, they are positive. And therefore, before subtracting the mean, you should compute the logarithm. And in many cases, you resolve the non-Gaussianity problem. So first of all, try to take the logarithm. And if it is correct, that's fine. If the logarithm doesn't suffice, there are other methods which we don't treat in detail. And these methods, there is an example of one of such methods in my slides. It's the normal quantile transform. It's not necessary for you to study on my slides how it works. It is just enough that you know that it exists. It's very easy. It's a very easy transformation, which has some operational problems because it is easy, but there are some operational problems. And I'm not going into details. Just note that there is, in any case, the opportunity to resolve the lack of fit. Again, with a preliminary transformation, because decisionalization is a preliminary transformation of the data. And in this case, what I'm proposing to do, taking the logarithm or normal quantile transform, is another preliminary transformation. Okay, before we go to some illustration with the PC, there is one important thing that we should take into account. These preliminary transformations are applied before we start the modeling. And therefore we actually, in reality, we apply the model not on the original data, but on some transformed data. So we are working in a different domain, which is a transformed domain, which is not a problem. The only problem is that when you use the model to generate your synthetic data, you obtain synthetic data that are referred to the transformed domain. So they are not seasonal, and they are Gaussian even if the original data were not. So it's clear that at the end of the simulation, you have to perform the anti-transformations in order to get back the data to the original domain, because you need synthetic data that are comparable to the observed ones, and therefore you have to go back to the preliminary situation. And this means that you have to anti-transform your data. So you have to apply back all the transformation, all the preliminary transformation that you did before starting. And apply back means, for instance, I have no more the formula for the decisionalization, but it means, let me write it again. I wrote y tj equal x tj minus sj. Let's concentrate just on the decisionalization of the mean, which means that when you generate your synthetic data are y's, and therefore to each data, in order to anti-transform, you have to add back the seasonal component. So the mean value refers to the same day. This is the meaning of anti-transformation. And if you computed the logarithm to make the data Gaussian, you have to compute now the exponential of your synthetic data in order to get back to the original situation. What is important to do, what is important to note is the following question. If I had to perform two transformations to make the data stationary and Gaussian, what should I perform first? Should I perform first the deseasonalization, or should I taking first the logarithm if I want to make the data Gaussian? The reply to this question is it doesn't matter in principle. The only thing that matters is that two things. First, if you want to take the logarithm of your data must be positive. And therefore, if you deseasonalize the data, you can get some data that are negative. So, in this case, if you decide to use the logarithm to make the data Gaussian, it's better if you take the logarithm before deseasonalization. So this is a very practical consideration. So it doesn't matter, but if you have practical needs, operational needs, of course, you have to take them into account. Second issue, which is very important, it doesn't matter the order of the transformation, of the multiple transformation that you have to take, but there is one thing that matters a lot, which is the following one. At the end, when you anti-transform the data, you have to perform the anti-transformation in the same order. So, if you first took the logarithm and then deseasonalized, at the end you have first to add back seasonality and then take the exponential. So you have to respect the order, which is trivial. If you think about inverting the order, it's meaningless. But we all know that the trivial things are the more important ones. Trivial things are the ones that if you make them wrongly, we are allowed to make mistakes when we do complex computation, but we are not allowed to make mistakes when you do simple things. Okay, I think that's it. Let me see. Okay, there is the cable and now let's try to provide some examples. It's better if I okay. Okay, so let me refer again to the time series of the Po River at Ponte Lago Scuro. And this time series, just to give you, I think I already plotted it, but let me give you, just show you the plot. The series was observed between 1920 and 2009, so it's 365 observations times 90, which is the number of years. And let me just show you here it is. It doesn't say much, but just let's have a look at, this is Ponte Largo-Scuro. Ponte Largo-Scuro is close to Ferrara. Conventionally, Ponte Largo-Scuro is adopted as the closure section of the Po River Basin. The contributing area at Ponte Largo-Scuro is about 70,000 square kilometers. You see that the maximum is about these are mean daily values, not peak flows. So the maximum is close to 10,000 cubic meters per second. Okay, let me show you, and probably, maybe I already plotted it, the autocorrelation function, and up to the lag of 730. This is the maximum lag to which I want to compute the autocorrelation function. Here it is. So let me make a comment now. The autocorrelation function, I think I already commented this with you. You see that has a peak around 365, which is the annual cycle, and the peak is given by the fact that seasonality is present. And seasonality makes the river flows observed to 1 year of distance very similar, and therefore causes the presence of a peak in the autocorrelation function. Conversely, for delay of, not conversely, in the same way, for a delay of about half a year, you have another peak. And the reason is that our weather has the river regime has two peaks, which are about 6 months far each other. And therefore, you see a similarity of the river regime after 6 months. And this is the reason for this peak. Conversely, I was saying you see some minimum in the autocorrelation function for delay of about 90 days and 270. Because these are the two drought periods. So this gives to me the opportunity to make an important remark. When you see periodicity in the autocorrelation function, this is a clear sign of seasonality. So in order to check if seasonality is present, besides your perception, you have to use the autocorrelation function. This is an autocorrelation function that cannot be modeled with an autoregressive process, because these periodicities are a non-stationary behavior, clearly show that there are non-stationary behaviors. So if we want to estimate an AR1 model on the Po River time series, we have to deseasonalize the data. Let us try to deseasonalize the data then. And first of all, we have to compute the seasonal component. First of all, I have to put the data in a matrix form, as I said before, where I have the columns represent each year. So let's put the data then in a matrix form. This is a name of a variable that I just invented now. And let's say that this variable is an array which is given by the Po River time series, and then we have to specify the dimension of the array. The dimension is, let's try with 36590. The reason why I said let's try is that I never remember if I have to put first the dimension along the yearly direction or invert the dimensions, or one should wonder here, should I put dimension 365,90 or 90,365? Let's try in this way and then we make a check. Okay, this is the array, which keep in mind that if I specified wrongly the dimension of the array, it would not be correct. So I have to be, and the program doesn't tell me that there is something wrong. So I have to be sure, I am sure that this is the correct dimension, but let's make a check. Let's compute the length of the series minus 365 times 90. Should be 0, fine. Okay, so make this check, because otherwise the program doesn't tell you, be careful that you made a mistake. Okay, now we have to check that the dimension was specified correctly in terms of order of the two numbers. And let me just check what are the first 10 numbers, of my time series of the Po River. So the first 10 numbers are these ones. I should get the same sequence of number if I now indicate here 10, 1.10, 1, which means one for the one here for the first year, because you see I put in the dimension days and years. So if I now ask the program to plot the first year of data, I have to put 1 year. And the days as first dimension, from 1 to 10. I should get the same list. If the list is not the same, it means that we mixed up. It's the same, so it's fine, okay? At this point, if I want to estimate the average, for instance, of the data for the first year, I just can type down mean PR10, comma 1. This is the average of the data for the first year. You see? Let's just, we are curious to see the second year. You see the variability. The variability is it's a factor of it's half. Let's see the third. Let's see the fourth. You see? The fifth. Just to have an idea, the mean of the whole time series is about 1500. But you see that in the individual years you have a lot of variability. Okay, now let's compute the seasonal component. Now we have to compute the mean in this way. If we want not to estimate the mean value along 1 year, but I want to estimate the mean value of the 1st of January, that's it. Because it's 1, so first day, you remember that I put as first index 365. So if I put 1 as first index is the first day, and I didn't put any index in the second place, which means that it's computing over whole the 90 years. And if I make now January 2nd, you see that the mean is very close, of course, because now I have to memorize in a vector all the means from 1 to 365. So let me write PR11 equals 0, and then I write a fourth cycle. I just brought PR11 equals 0 because I need to define the variable. Now let me write the fourth cycle for E in 1 to 365, and then I can write PR11 I equal mean PR10 1 dot. Good. This is the computation of the seasonal component. Let us plot it. Plot PR11 type equal line. And let's see, no, there is a mistake here. Yeah, the mistake was, let me go back. The mistake was here. This is not 1 but I. Okay? This is correct. Now plot. Here is our seasonal component. You see that there is some variability, which is, as I said, not really meaningful. Even for the Po River, which is a river that is slowly varying in terms of river flows, you see that there is some variability which is not really meaningful. And let me show you a smoothed version of this diagram. The same diagram smoothed. Okay, let me see. Here it is. Okay, this is a smoothed version, much better, but it was derived from the same, I show you. The diagram that we obtained is this one, and now this one. It's similar, just smoothed. You see, we arrived at 2000 here, in the other one 2000 in the same way. What is interesting to note is that this peak here, which is given probably to snowmelt from medium altitude mountains, and it's occurring about end of March, beginning of April. So the Po River at Ponte Lagoscuro has a first increase due to snowmelt, and then a not really significant decrease, and then there is the contribution of the pluvial regime and also the contribution from melting glacier. Okay, Now, let's go back to R. We obtain this PR11, which is our seasonal component, okay, which is here. Now, let's compute the deseasonalized series, and in order to compute the deseasonalized series, what we have to do is to subtract, I repeat, to any observation the corresponding mean. The easiest way to do that is to repeat the seasonal component PR11 90 times. I just repeated the seasonal component 90 times in this way. REP means repetition in R, and then I can compute the deseasonalized series as the original series minus the repetition of the seasonal component. Now let's look at the autocorrelation function then, because this PR13 is the deseasonalized Paul-Ever series. Let's look at the autocorrelation function, because it should be no more periodical. So ACF PR13 lag.max equal 730. Here is the autocorrelation. You see, it's fairly okay. There is still something irregular here, because there is still some seasonality left. But you see that the result is satisfactory. It's an autocorrelation function that is now quite okay. And now let's forget about Gaussianity. This is not Gaussian, this time series, because let's just make a check. If I make plot density PR13 type equal line, this is just plot of the sample probability density. Let's have a look at what we obtain. You see, it's clearly not symmetric. I could take the logarithm, but the problem is that I already deseasonalized, so I cannot take the logarithm. So let's forget about Gaussianity for now. Let's move forward anyway. Okay, now, next thing that we should do is to calibrate the autoregressive parameters. And to do so, we need to write down a routine, a function of R that computes the epsilons depending on a trial value of the coefficient phi. Let me explain. I need to start back from the general formulation xt equal phi1 xt minus 1 plus epsilon t, and I mentioned to you that one way of finding the optimal value for phi1 is to minimize the sum of squares of the epsilon. And if you remember, I made a sketch on the blackboard for performing this estimation in Excel, and I said I need to estimate the epsilon as the difference of xt minus phi1 xt minus 1. Therefore, I have to write a routine in R that computes the epsilon and then computes the sum of the epsilon t squared. And then I have to find the value of phi1 that minimizes this sum of squares. So I have to write a routine in R, again, that computes this sum of squares. And the last time I got trapped because I tried to write the function directly in R. This is not a good idea. The ideal thing to do, given that a function is a program, is to write the program separately with a text editor or with Word if you wish. So let me open a text editor and try to write the program separately. This is a text editor that I use with Linux, but you can use, for instance, Notepad if you are a Windows user. And let me call the function AR1, which is a function whose unique argument is the coefficient phi1. Okay? We could also write phi1, no problem. Then let me put a parenthesis, and now what I have to do is first of all, let's define a variable which is the vector, or let's say in this way, is a repetition of 0 for 365 times 90 times. This is the vector of the errors, of the epsilon, which I need to define before starting. Then let me compute the errors. I think the only way is a fourth cycle for I in 2, because you remember that I have to start from the second time step, 2 365 times 90. This is my fourth cycle. Let me open a second parenthesis, and then we can write here 20 equal. I don't remember the name that I used for the decisionalized series. I think it was PR13. PR13 I minus PR13 I minus 1 multiplied by phi1. This should work. This is my epsilon. Yes. Should work. Then here I can compute sum of squares equal sum here 20 squared. Let me see if I can increase the font here, because sorry, I forgot. Should be able to, but let me see. Let me try with the easiest way. No, it doesn't work. Probably. Preferences. Font. Let's see. Okay, a bit better. A bit better, yes. Then return sum of squares, and that's it. This should work. If I cancel the spaces, let me see, should work. Okay, but in order to see if it works, let me, okay, here I forgot an I. Is it readable? Yes, more or less. And then let me copy it. I just copied the instructions, and then I paste the instructions in R. I go back to R. Here it is. It seems that there is no error, but in order to see if it works, let me try AR1 0.5, and let's see. This is the sum of squares. Let me see 0.6. Okay, should be correct. 0.7. Okay. Now we have to check. So again, this is the function that I wrote that computes the errors and then takes the sum of the squared errors. and the only argument of the function is phi1. Now, given that it seems that the function is working, now we can try with an optimization routine. Let me start again. Optim AR1. Let's see. I think I have to give a starting value and for the coefficient and the name of the function. Let's see if it works. Yes. And let's see what happens now with the optimization. Which means that now R is looking for the value of phi1 that minimizes the sum of squares. Okay, let me go back because there are a lot of issues. Okay, and here's, you can see the parameter, 0.9680664. And what you should understand from here is that the coefficient is close to 1, so it's not a good sign, because it's close to the limiting value for stationarity. This is not a good sign, but in any case, this is a value for the coefficient, and let's keep it in mind. Let me copy it, sorry. Now what should we do? Because the model is parameterized, and now what we should do is to check if the assumptions are satisfied. The first check that we have to make is the autocorrelation function of the error. This is the first check. I foresee that, I predict that the assumptions are not satisfied because the data were non-Gaussian, and I have seen the coefficient that is close to 1, but in any case, let's make the check. To make the check, now I need to go back to the function that I wrote here, and to tell the function to give back to me not the sum of squares, but rather the error. Because now I need the error. The vector of the error. Sorry, I don't understand for what reason when I select it disappears. So, this is the function that I corrected. Let me paste it in R. And now let me compute the function for the optimal value of the parameter. So AR1 for the optimal value. This gives to me the vector of the errors, and let me put the vector, keep the vector in memory. Let's have a look at the error. Here it is. There are some spikes. This is quite normal when the data are non-Gaussian. But let's have a look at the autocorrelation function, which is the thing that is most important for us at this stage. So ACF, here 30, and lag.max equals 730. Here it is. Okay, let's have a look at this autocorrelation function. It's not bad, because you see that there is indeed a huge difference with respect to before. And what are these blue lines? Are confidence bands for the null value, which means that they are computed in some way which is not relevant for us now, but I already discussed with you these bands. What is important for us is to note that ideally we would like the autocorrelation function be included within these two blue lines, and the results are not bad for the high legs, but there are problems with the low legs. Why there is this negative correlation? There is this negative correlation because in order to fit the remaining part of the autocorrelation coefficient, the AR1 model basically overestimated the autocorrelation in the first lags, and therefore it was overestimated to the point that once that the model is applied, the error has negative correlation, which means that the model overestimated the original correlation. And this is, of course, a sign of limitation of the model, a limit of the model. it can be due, this lack of fit, to lack of a reliable assumption, or inability of the model from a structural point of view to fit the data. Therefore, the first thing that I would do is to make the data Gaussian, and the second thing is to increase the autoregressive order, because AR1 process is not complex enough for this kind of time series. But in any case, you see that there is we made good step forwards, because if you remember the original autocorrelation, it was in the first lag, it was here you have a negative coefficient of minus 0.2. At the beginning, you had a positive coefficient of about 0.9. So the model was indeed successfully removing part of the correlation structure in the data, but there is still some correlation left. One final remark, you see that there are some small cycles. You may wonder what these cycles are. Especially in the first part of the autocorrelation function, you see that there are small cycles, up and down, up and down, up and down. This is a weekly cycle. Why a weekly cycle? Because in the Po River, there is a significant impact of the release from the artificial reservoirs. And the release is managed accordingly to the request for hydropower, and therefore during the weekend, when you have less request for hydropower, they don't release. And this is the reason why you see a weekly cycle, which is interesting, because you see that statistics indeed helps you to understand the physical behavior of the system. This means that there is still no stationarity, not only for the yearly cycle, but also for the weekly cycle. So a second decisionalization will be needed to remove the weekly cycle. Indeed, this series of the Po River is known